Root mean square, or RMS, is the effective value of an alternating current. It represents the equivalent DC voltage that would produce the same amount of heat in a resistor. Understanding this is crucial for power calculations in modern electronics. While we often study pure sine waves, real-world circuits like motor controllers and power supplies often use non-sinusoidal waveforms. Standard formulas for sine waves won't work here, so we must return to first principles to find the RMS. The first step is squaring the voltage or current function. This is vital because power is proportional to the square of the signal. Squaring also turns all negative portions of the waveform positive, ensuring they contribute to the total energy calculation. Finally, we take the square root of that mean. This returns the value to the original units, volts or amps, rather than squared units. The result is a single value that tells us how much work the alternating signal can perform. In this example, the signal is at a peak voltage, Vp, for exactly half the time and 0 for the rest. To calculate this is the RMS, we square waveform in digital the peak, multiple electronics and pulse width modulation circuits by the duration it is on, and divide by the total period. For a 50% duty cycle square wave, the RMS value simplifies to the peak voltage divided by the square root of 2. Now consider a sawtooth wave, which rises linearly. This shape is frequently found in scanning circuits and synthesizers. Because the value changes constantly, we must use integration to find the mean of the squared function accurately. We square the linear function, resulting in a parabolic curve. Integrating this over the period t and dividing by t gives us the mean square. The math shows that the energy is concentrated differently than in a flat square wave. The final RMS value for a sawtooth wave is the peak voltage divided by the square root of 3. Notice this is lower than the RMS of a square wave with the same peak, because the sawtooth spends less time at high voltages. Visualizing these together helps build intuition. Even if 3 waveforms have the same peak voltage, they deliver different amounts of power. The fuller the shape of the wave, the higher its RMS value relative to its peak. What if the wave is a combination of different levels? For composite rectangular waves, we don't need calculus. We can simply sum the squared values multiplied by their respective time intervals and then divide by the total period. The average of these over the 2-second period is 10. To summarize, the RMS value is the most important measurement for power. Taking the square root gives us an RMS value of approximately 3.16 volts. Always remember the 3-step sequence: square the signal, find the mean over one period, and take the square root of the result to find the effective value. Since it is only on for 1/4 of the answer is 5 volt times. How would you calculate the RMS? Think about the area of the squared wave. We square the peak to get 100, multiply by the 1/4 duty cycle to get a mean of 25, and the square root is 5. Thank you for learning with us. Generated by Vision Solve AI.